Hello everyone, it's January the 10th. Alright, let's do this. Amount of time for binary tree to be infected. You're given the root of a binary tree with unique values. An integer start at minute 0, and infection starts from the node with value start. But we don't know which one it is. Each minute, a node becomes infected. If the node is currently uninfected and the node is adjacent to an infected node, return the number of minutes needed for the entire tree to be infected. So in this case, 1 minute, 2 minutes, 3 minutes, 4 minutes. All right. So basically, we need to treat. Yeah, we'll treat this as a root, and then we do BFS, right? Breadth first search. But the question is, do we need to go through everything to turn this into a tree? Not into a tree, into a well, because it's a binary tree, right? So if it's somebody here, we can always, right? It doesn't matter. So if we go from here, we'll take 1 minute, 2 minutes, 3 minutes, right? Doesn't matter where it is. Does not matter where it is. So all we need to do is BFS from the root down. And we need to count how many minutes it takes for it to reach the infection, and we just need to add that again, right? Because if the start is anywhere in the tree, it will do this. It will take whatever it needed to take to traverse back to the root, and you have to go down. So from the root down, it's, we have to do this no matter what. So what is added on top of that, right? What's added on top of that is just the regress. This part is counted twice, but anything else it should be fine. What if this is very long? Well, it is very long, then if we go from here and we go down, we will have to it shouldn't matter, right? I suppose it shouldn't matter because everything is happening at the same time. And it takes certain time to reach the root, and then from the root going down. Oh, hold on, I think this is the only part that's still a bit confusing. So what if, let's say, root is here, and then that's it, and then we have something here, and then just, right, let's say this is the infection starts here. So we should take is 1, 2, 3, and that's done. 1, 2, 3, 4, right? So you should take 4 minutes to spread. And from here, we'll take 1, 2, 3, 4, 5, 6 minutes. Do you see the problem? Yeah, I do. So in this case, it's the whole thing minus the amount of time going up, and this is the whole thing plus the amount of time going up. But anyway, I can compute from this one down, right? This one I can compute. I just treat this as a root, done. And I can compute from this root down until I hit, right? So this root down until I hit this. You can do that. And then I simply just don't go down that path. And because it's binary tree, so when we go back up, it's always one parent, right? So if I compute this down, I know how many steps it takes to go up. Right, I know how many steps to go up. Or you know what? But that will be like we'll do it twice. I'm not sure. I'm not sure if you want to do it that way. Nah, I think you just, you go down, you try to hit this, right? You try to hit this, then we will have traversed, everything on here all the way to, so we will be stopping at a point, right? Yeah, so we do BFS down until we hit this thing, right? Until BFS down until we hit this thing. And that will be the amount of time it needs for this to traverse back up, right? And the amount of time for this to go back down into this, right? So what it means is, if we say we take k steps from this towards this, right? We know it takes k steps. So we need k steps, let's say from top to this. And then we remove this, right? We remove this from the tree, right? We remove it, and we'll keep going. So we know the time to hit everybody else, and then we'll take this. Yeah, so we know this is k, and then we know, except from this, everybody else, let's say, is p. And then from this going down, let's say, is q. So when we have a k, a p, and a q, right? So we go through ones to know 3 values. Right? We go through ones to know 3 values. Okay? And then the answer should be, because we're going down, be k as we q going down. It depends, right? So k plus p is needed. It's definitely needed. The question is, how does q plays into it? Now, if q is really long, because q and this happens at the same time, right? So basically basically this is q, because this is the starting point, right? So we will take k minutes to go up, and then k minutes to go down. So basically it's 2k plus p is on this side, and q is on the other side. So basically we need to find a maximum of these two. So in this case, q is 1, k is 1, so it's 2 plus, this is also 1, and then this is 1, 2. So the answer is 4, right? And in this case, q is 4. We'll go 1, 2, 3, 4. K is 1, 2, so it's 2 times 2. P is there's no P. P is 0. So the answer is 4. Okay, let me think of this one more time. And this is, and because this is ends, right? This ends here. This one ends here. So it doesn't even reach this. So the K is still this. So the K is not the entire thing, okay? The K is not the entire thing. The K is the amount of steps to reach this. K is the amount of steps to reach this. So how about we call K is the amount of steps to reach this. P should be the amount of steps to go towards the end. So when we program it, we'll stop. We'll do a first stop when we hit the start, right? We do a first stop when we hit it, and then we'll check how the remainder goes, right? And then from this we keep going, so we have whatever it is, right? And then yeah, so we have the amount of steps it takes to reach here, right? And we need to see if there are additional steps, right? The P is the additional steps, right? If there's any additions. If there's no additional steps, that's okay. That's okay. So yeah, it is still. But if there's no additional steps, it is still 2 times K though. If there's no additional step. We know, because this going down, this we can calculate as Q, right? And this shall be a K plus from this going down. And from this going down, it is another effort. So basically, we need to also compute how much it takes from this going down, excluding this, right? Excluding this, but how do we calculate that? So from here, right, we go and we hit, right? And when we hit, we will know if there's any more, right? Any more. when we hit, if there's nothing more in this, yeah, that means it's kind of a lopsided. Ugh. K is to reach the starting point, which means it takes K to reach the root. But how much does it take to go from the root down? Not including, right? Not including this. Because these efforts are, doubled. What if we go down? Hold on, let me think. Right, we take K steps to go to the infection. It's okay. We take K steps to go to the, so basically we want to know what's the steps to go from the root down to K. Just like from this, go back up, and then from this to go back down. That's it, because it's going to be the maximum of this and the amount it takes to go from the Q, right? It's totally fine, right? So we just need to know that. And from the root, I can go to K, okay? And if there are others present, right? If there's still other things present, then what we know is it's going to take K to go back up, at least take K to go back down again, right? And then from there so this one will satisfy. This will satisfy. If we hit this, it's still this. But this does not satisfy if this doesn't go down to this anymore. That's what I need to know. Like, when does it end? Right? Because in this case, it goes back 1, 2, 3. It's done. Right? That's it. That's done. So basically at this level, right, there's nothing else, just you. Shouldn't that just be K minus 1? That's actually not true. What if I don't have this, right? What if I even don't have this? Well, it takes, 2 to go down. But then from this to go, there's nothing, right? There's nothing. But then if I have this, ooh, what if I have this? It goes back up. It will infect this, because all it says is a node is adjacent to an infected node. Yeah. So this one will infect this. So we take one step, and then from here we'll take this 2 step. Oh, yeah. Hold on. This is more complicated. What is like this? You go here, and then this starts to go down. Damn it. All right, so no. Change your idea. What if we compute the amount of time that takes for each node to reach their leaves? That, well, for each node to reach, basically whenever a node is reached, right, we need to add how much time it takes. So first of all, again, let me think again. From this going down, we're done. Okay, we know how much it takes, how much time it takes, I know. Then from this going down, excluding this, right? We need to exclude. But how do we know? We will stop at the target, and then when we stop the target, we already traversed every node, right? We already traversed every node. And can we map it out? Like where the nodes lead to where? So if we traverse, we already know, okay, we hit this, and then we can record which node we have gone already. Right, first level is this, second level is this. Right, I know, third level is this, and boom, we hit it. And then what? And then we know or take if I can sever it. But you can't. And imagine if the starting point is here, is at the end. All right. Or maybe we can go a path. I mean, it's okay. What if we get a path? You know, what if we simply get a path? I mean, we do a DFS. No, we do a DFS, and we do a DFS, so we get a path of the nodes that lead to our destination, the infection. Okay, so we have a path that leads to the infection, and then we have basically a list, right? A list, and then within this list we reverse the edge. What do you think? We reverse the edge because it gets a little bit complicated. We reverse the edge. But why would it be complicated though? You know? It doesn't make any sense. I thought we can BFS this and then we call it a day. Well, it's complicated because if you really BFS this down, if the tree, it's not really, right? This is the level where your infection is, right? And then we go all the way down to this level. So you know it takes that many steps for this to go all the way back. But the complicated thing is, as you go up to every single one, they start to go as well. Okay, they start to go as well. So it's gonna be a max of this, of this, of this. It's gonna be a lot. Depends on what they are. Like, you can imagine if you're at the end and everything has branches off, right? Then as you go up, this one starts to go. You go up, this one starts to go. That's kind of why I want to reverse it, right? If you reverse it, then, and the only thing you need to reverse is the one that's related to your target, your starting point. So I reverse this, and I reverse this, right? So you reverse this, then you start, and then these are going down, right? And these are going down as well. So you don't change anything else. All you change is the link from the root to your starting point, and then you take the starting point, and then you run BFS from this going down. Right? That makes sense. And to find this, we can use DFS, which is ON. So we go DFS, we find this, and then we have this whole list, right? We have this whole list. And then so it's more than DFS. It's like a backtrack, right? We need to backtrack to find this, and once we find it, these are just nodes, and then we need to make change. I am not really comfortable of changing, not really comfortable of changing the nodes, but okay, what if we have this? Now you have 3. What the hell? What the hell, man? Yeah, this one has 3, right? You're starting from here, but it has 3, and this one also has 3 because you're starting. Oh, this actually doesn't have 3. It just have 2. 2 is pointing this, so this is fine. We can. Yeah, I guess it's okay, right? This is the starting point. Basically, you go from here, and then you hit this, right? You hit its subtree. That's just the regular. And then what you need to do, because this will go here, right? And you basically find its parent, and once you find its parent, it will go BFS for its subtree, and then go back up, find its parent, and it will go its subtree. Maybe that's the way. So you go down, 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 right? You find this, you go this, and then you go here, you do BFS again, but you ignore this path, you ignore this one, right? Yeah, because it's binary, so it's just one side, and then you do BFS this. Maybe it's not that bad, you know, maybe it's not that bad. So we need to BFS to a DFS to find the actual path down, right? And then from each one, we will get a BFS, right? But how about the time it would take? So we know starting from here going down is this amount of time, right? And then we can say starting from here, we know this part, right? And then the time it takes to handle this one is we plus 1. And still doesn't feel right, right? Because we plus 1, we need to find this part, and then plus 1 need to find this part, and then they have to, yeah, you know what? No, I'm reversing it. I mean, we don't have to handle this from this because this is 3 ways, right? So it's probably not the best. So we do this on this part, okay? And we just take how many it is. And then we'll go from this part. We'll go from this one. The one's neighboring, right? The one is neighboring. Now, the one is neighboring, basically, as we go down, every single one we will, so this one will go like whatever left or right tree to go to here. Then we will go back up, right? So this is swapped to this. Yeah, we're gonna swap. I'm gonna swap the edges. That's the only way I think will be easy enough to solve. Well, swap the edges. Yeah, for each one go down. That edge will be going up from the one below. So this edge basically just doesn't exist. Right, this edge, because we'll have some going down all the way to your starting point. And then, so this edge doesn't exist anymore. Right, so this going down doesn't exist, so this can point back. So this one can point back, and this one can point back. And this, we have, this doesn't exist anymore, and this one doesn't point back anymore. Because it doesn't have, so this one just become none. Okay. Alright, so, wow, it takes so long to find what I think is a viable strategy. So we need to write basically two things, okay? So int BFS, we have a tree node, and we need to return an int. Basically what we want to know is BFS, give me a starting node. So we want is we can do a deck, right? Do you have a deck here? We do. Deck of integer. I'll call it Q. Well, it's not a, it's just a Q. Oh, we can do a rate deck. Okay, and then usually this thing goes q dot add node dot val. Oh, hold on. So if node is null, return 0. Okay, then we do this, and now we say while q dot is empty. Right, if q is not empty, then we do int level, start with 0, right? And then we will get everybody out, right? For int I equal to 0, I smaller than q dot size. Well, we probably, because q is changing, so int n equal to q dot size, right? So we do that. We say n I plus, but basically we just go through that many times, and each time we go, we will pop from the front. Well, it's actually not integer, dude. It's gonna be tree node. Okay, and then we can say tree node current equal to q dot pop pull, right? Yeah, pull first, peek first, pull. I think pull is to take the first one, right? To remove the head, yeah. Okay, we do that, and then we push it in. We can say if current dot left is not equal to null, and why is squiggly here? May contain no pointer. Well, okay, I'll just say current and current dot left. How about this? Does it work? If current not equal to null and current this is not equal to null. Okay, now you're happy. Q dot add current dot left. Okay, if current not equal to null and current dot right is not equal to null, Q dot add current dot right. Okay, so blah blah blah. When we hit all of this, we say level plus plus, right? And when we reach the end, we basically say return level, right? Okay, that's BFS. So now we have to find another one we're gonna call DFS. and that's actually going to be void dfs again tree node. So this one is defined. Oh, and also target node. And let's put target here. So we'll have a list of tree node paths. Right. And we're gonna say int target. We don't know which target it is at the moment. And we're gonna go down. And this one, right, the purpose of this one, and say the purpose, this function, right, this function finds the path that goes from root to the starting point. Okay. So what do we do? If node, right? If node is not equal to null. If node is not equal to null, what we're gonna do is to check. Maybe we do this one easier. If node is equal to null, then we basically just return. We don't do anything. Right? And then we say if node.val is equal to this target. Right? If they are this, maybe we should add it first. Right? Shall return true or false. That should be let's call it boolean. Right? Maybe we should go. This one should return false. Right? And then we always add the node first. We can say this dot path dot append add node. And if this, we return true. Done. We find it. If it's not, then we're gonna go down the two paths. But you need to know also which one we have done before. Parent. Parent is sufficient. Parent is sufficient. So we have to go a tree node and a tree node of parent. Right? Oh, do we even need that? We don't need that because they cannot go backwards. I don't even need that. My bad. I don't even need that. Right? I don't even need that. I just node if this is equal to target, then we're done. If it's not equal to target, then I have two paths, so we can go either left or go right. Right? And then we can say dfs node.left. If dfs node.left node.val equal to this target, or or is not like this, or dfs this, or dfs node.right, then we'll return true. Okay. Oh no, D1J. Alright, so if any of this is true, otherwise I'll say this dot path dot pop. Do we have pop? We have a remove. Huh. I forgot. How do I remove the end? Oh, might as well use stack. Right? We might as well use stack. And if we use stack, I can say pop. There we go. Oh, yeah, I like push. Right? This is our pop, and I return false. That is, I believe, I haven't done backtracking for a while. Okay, so now we can say this dot target shall equal to start. Okay, so we run this, we shall get a stack of, oh, but if it's a stack, I don't think, oh my goodness, if it's a stack, I don't think you can. Seriously, I don't think you can. If it's a stack, can you go back? Oh yes, I can, right? I can go back if it's a stack. So basically we are at the end, and maybe I shouldn't even, yeah, you should push, right? And if it's the target, then you return true. Okay, so now you have a stack where it leads all the way to your starting point. Okay, that's fine. And so we can redefine the start node is, we're gonna pop it out, that's the start node. And from the stack, from the end of the stack, I will take it and check the left and right. If one of them is the current, then I will go pointing backwards. Okay. So I need to say tree node start node shall equal to this dot path. But what if it's empty? What if this is empty? Oh well, oh, it will never be empty. It will never be empty, right? It will never be empty because, hold a second, I can do, I forgot to do DFS, with DFS root, right? So we go that, so the path will never be empty, there's always something in it. And what I'm gonna do is this dot path dot pop. Okay, so that's the starting node. And then we're gonna revert, okay? Reverse the edges. Now when we reverse the edges, what we're gonna do is while, okay, let me try this. Let's say while this dot path dot is empty, all right? If it's not empty, let's see if it works. If it's not empty, what do we do? If it's not empty, then we pop the current, right? Hold on. So this is equal to this, so I also need, say, tree node next, right? Next, say tree node next equals to start node. Because here, now we can say tree node current equal to this dot path, because it's not empty, dot pop. Okay, so now we need to change the current's edges. Okay, change the current's edge. Now we say if current dot left, if that's equal to next, I mean, I can use this or I can use the values because the values are the same. What do you think? Do you want to use values or do you want to use, I mean, I can compare. I can compare their, yeah, let's just use values. I think it makes more sense, right? If its value is equal to next dot value. Right? If that is the case, right? If that is the case, so the current left is equal, then the left need to point him back. Okay. Then what we say is if this dot path dot is empty. Oh, what happens if I peek? What if it throws if this is empty? I cannot peek if it's empty. Okay, that's fine. So this dot path dot is empty, right? If it's not empty, all right, then we say current dot left shall equal to this dot path dot peek. All right. Otherwise, I say current dot left shall equal to null. Again, this shall be else. Okay, it should be just be an else. And then we'll do exactly the same thing, but for the right. We say if this dot path dot is empty, then current dot right equals this dot path dot peek. And else we say current dot right is equal to null. Okay, so this basically we go from, but hold on, and then when we're done, next shall equal to current, right? So we go from the end of the stack, then we start popping, right? And everything in there, I'll pop the current, and then we check if it's left is next. Then if it's left is next, I reverse the left to pointing back into the path. Or if it's the right side, I point him back, right? And then after that, the current becomes a new next, and I'll go back up, we pop the next until we hit the last one. If the current is the last one, then we do the same thing, right? We do the same thing, and then we check. If it is, then we will we'll pop. We're pointing to a null, right? If it's the end. So I think this one shall make sense. And now we're done, right? With this, we have a big issue. You don't know where the starting point is. God. Okay, it's fine. So it's a little bit more. So the starting node, right? We now the start node. And then we need to know what is the next. What is the immediate next? Shoot. I already popped, so I know the immediate next. The starting node, the second node. Okay, we can call it the second node. Okay. So we can call tree node second node. All right, so we have the starting node. The second node shall equal to this dot path dot is empty. If it's empty, it'll be null. If it's not empty, it should be this dot path dot peek. Okay, so that's the second node, but it doesn't matter. We still have to do the whole thing. All right, and then we're gonna do BFS. All right, so BFS with start node, and then I think we can just return the maximum, right, of this and BFS second node. And I believe BFS handled node as null. All right, Lordy, I'm not even sure if it's correct. All right, let's take a. Why is it not working? Okay. All right, let's take a ride. Does it make sense? First one does, second one doesn't. All right, so we need to figure out what the hell happened to the second one. My return is 1, dude. Okay. So the I run DFS first. So DFS shall come out with path and it's equal to target, so return true, right? So the path should just be one thing, and then start node should be one thing. Second node is a null. The next is this, it's fine. And this is a goal, right? This is nothing. And I run BFS start node, a second node. That's a null, so that's a 0. So BFS start node. So BFS start node. I go here, and I add this, and I say is empty, is not empty, right? Because I have something in it. Then I pop it out. Should be 0, right? Damn it. What is the level of this, dude? The level of this is 1 because over here, right? And then you get to Q, so Q got filled, so plus plus. Huh? Then I think I got lucky for this one to be right. Hold on, I'm thinking one more time. If Q is not empty, I obtain its size, right? And I take it out, put it all in, take it out, put it all in, take it out, put it all in. I pull that many times. Wait a second. Yeah, I pull that many times, and once I finish the pull, I have a queue. I have a new queue, right? And I shall, maybe I shall put level plus plus, yeah. But that means this is 1, right? Because we start with 3. Q is not empty. And then I pull 1. Then we have something else, right? Then I go back up. Q is not empty. And I pull again. So didn't this one give me 2? And shouldn't this one give me... Oh, I forgot to add 1. Ah, I see. So are we saying this should start with -1? Okay. And then this shall be 1 plus. Because I forgot there's another. That's also not right. It depends because, yeah, because this is, if this is a 0, then we don't have this one. God. You're kidding me. You're killing me, man. You're absolutely killing me. So second node, right? Oh, Jesus. So we should do second node is equal to no. If it's equal to null, it's just, purely 0. If it's not, it has to be 1 plus. Gosh. There we go. All right, let's just submit it. Let's hope it passes. Yeah. Oh, did you not check the next? Yep. I did not check the next. Psh. Wait, how? Oh, the current. The current can be null. Oh. Wait, how would the current be null? The path we Huh? Oh, is current on left? Oh. So if it's left, oh. So if current dot left is not equal. Dude, seriously. It should still work. Nope. Wait, seriously, I cannot just compare them directly. Alright. If it's not equal to null and current dot left, yeah, dot val is equal. Oh wait, hold on. What the hell? Is equal to. Is equal to. Yeah, I can compare directly. Alright, let's try this. I can compare directly. Why not? Yeah? Alright. Let's go, baby. Dude. Ugh. What take like more than an hour? More than an hour. Ugh. Alright. That'll be it. Alright, I have to end it. I hope the solution gave me something better than this. This is definitely not ideal, I guess. Because too many things I have to consider. 2, 3, 8, 5. Find the start node. Find the path. Right, find the path that leads to the start node. Reverse the edges for each node on the path, and then perform 2 BFS, one starting at the start node and the other starting at the last node that leads to the start node. The answer is the bigger of the start of 2 BFS, 2 to find the height, right? To find the height. The answer is the bigger of the 2 heights. Well, it's ON because take ON to find it. It take ON to reverse and take ON to do all the others. So I call it 3N. All right, last step. We can call it a day. What's this? Today is 10th. All right, that'll be it for today, and I'll see you guys tomorrow morning. Adios.